Hello everyone, my name is Vengala Sripriya and today I am going to present my Embedded Systems Internship project EV ADAS Dashboard, Real-Time Electric Vehicle Monitoring and Advanced Driver Assistance System using STM32 Blue Pill and PICSimLab. During this internship, I worked on developing an embedded application that combines electric vehicle monitoring with advanced driver assistance features. In this presentation, I will first give a brief overview of the project, explain the implementation, and finally demonstrate the complete working of the system through a live simulation. So, without taking much time, let's begin with a short introduction to embedded systems. Before discussing the project, let's first understand what an embedded system is. It is a combination of hardware and software designed to perform a dedicated function. Unlike a general purpose computer, it is developed for a specific application and provides reliable real time operation. Today, embedded systems are widely used in automotive systems, healthcare devices, industrial automation, consumer electronics, and many IoT applications. Since my project belongs to automotive domain, embedded systems plays an important role in monitoring vehicle parameters and improving driver safety. Now that we have understood the basics, let's move on to the project overview. Every project begins with identifying a problem and proposing an effective solution. In conventional vehicles, drivers may not receive timely warnings about nearby obstacles, blind spots, or important vehicle conditions such as battery status or motor temperature. To address this problem, the proposed solution in this project is to develop a real time EV ADAS dashboard using the STM32 Blue Pill microcontroller. The system continuously monitors important vehicle parameters, processes data from ultrasonic sensors, and generates collision and blind spot warnings whenever required. Finally, all the processed information is transmitted through UART communication and displayed on a Python dashboard for real time monitoring. Now, let's look at the main requirement of this project. The primary objective of this project is to develop a real time electric vehicle dashboard integrated with advanced driver assistance features. The system continuously monitors parameters such as vehicle speed, battery, state of charge, motor temperature, motor torque, accelerator position, brake position, and estimated driving range. It also uses three ultrasonic sensors to detect nearby obstacles and implements features such as forward collision warning, blind spot detection, fault monitoring. All the processed information is then transmitted to a Python dashboard through UART communication. Now let's understand how all these modules are connected together. This slide shows the overall architecture of the EV ADAS system. At the center of the system is the STM32 Blue Pill microcontroller board, which acts as a main controller. It receives the input from the sensor process, the EV control, ADAS, and fault management modules, and sends all the processed information through UART communication. Finally, the Python dashboard displays all the vehicle parameters and warning messages in real time. Now that we have seen the overall workflow, let's look at the development tools used in this project. To implement this project, I used several development tools. First of all, STM32 Cube ID was used for firmware development and generating the binary file. And the PICSimLab was used to simulate the STM32 Blue Pill hardware and connected peripherals. And the STM32 Blue Pill board is the main controller. And VSPE was used to establish virtual serial communication between the simulator and the dashboard. Finally, Python. It was used to develop the real time graphical dashboard. During the live demonstration, I will also use the Teratum to verify UART communication before launching the dashboard. Now let's have a quick look at the final output of the project. This is the Python dashboard developed for this project. It receives a real-time UART data from the STM32 firmware and displays important vehicle parameters such as speed, battery, state of charge, motor temperature, motor torque, driving range, and sensor readings. Under normal operating conditions, the warning status remains none. If an object enters the left or right blind spot region, the dashboard displays an advisory warning. Similarly, when an obstacle comes very close to the front of the vehicle, the warning changes to critical, indicating a possible collision. Now that we have seen the expected output, let's move on to the live implementation and demonstration. In the next section, I will briefly explain the firmware implementation, build the project, launch the simulation, establish UART communication, and finally demonstrate the complete working of the EV ADAS dashboard in real time. So let's begin with the implementation. So we have completed the project overview. Now let's move on to the implementation part of the project. Here I am opened the STM32 Cube IDE, which I used to develop the embedded firmware for this project. Before running the simulation, I will briefly explain the main modules of the firmware and how they work together. As we can see here, this is the project structure. The project follows a modular approach where each source file is responsible for a specific functionality. Instead of explaining every line of code, I will briefly explain the purpose of each module. Now, first of all, I will open the IOC configuration file. Wait a minute. So now this is our IOC configuration file, and in this project I am using the STM32F103C8T6 blue pill board, which is a 32-bit ARM Cortex M3 microcontroller. Using this configuration, I enabled the required peripherals such as GPIO, ADC, timers, and UART. These peripherals are essential for sensor interfacing, timing operations, analog data acquisition, and serial communication. Now, let's look at the firmware implementation. So, for that purpose, I will open the main.c. So, this is the main.c file, which is the entry point of the application. At the top, all the required modules are included, such as EV control, ADAS, ultrasonic, fault management, UART shell, EV control, and if we scroll down, we can see the initialization part as it is there. Now here all the software modules are initialized. The EV initializes the vehicle parameters. The HC SR04 initializes the three ultrasonic sensors. ADAS initializes the advanced driver assistance module. Fault initializes the fault management system. Finally, shell initialize enables UART communication for command processing. Now we can see here the main loop. The while loop is called the main loop in here. So this loop continuously executes throughout the program. First it reads the ADAS. First it reads the ADC input such as accelerator, brake, battery state of charge, and motor temperature. Then the EV module is updated. After that, the ultrasonic sensor data is processed, ADAS warnings are generated, faults are checked, and finally, all the processed information is transmitted through UART to the Python dashboard. Since the process repeats continuously, the dashboard receives a real-time updates. Now we can open the evcontrol.c. Wait. Now here We can see the three driving modes that are Eco, Normal, Sport. Each mode provides a different torque scaling factor. And next, this EV and next underscore read ADC. This function reads the accelerator pedal, a brake pedal, battery state of charge, and motor temperature through the ADC channels and converts them into meaningful values. Now here we can see the EV update. This is the core logic of the electric vehicle model. Based on the accelerator input, motor torque is calculated. When the brake pedal is applied, regenerative braking is activated. Using these values, the firmware calculates with vehicle speed, battery, state of charge, power consumption, estimated driving range, and motor temperature. These parameters are continuously updated during vehicle operation. Now let's move to the ADAS module, which is responsible for driver safety. So here we can see the ADAS update. So the firmware receives the distance values from the three ultrasonic sensors. Using the front obstacle distance and the current vehicle speed, it calculates the time to collision. Depending on these values, the system generates forward collision warnings. It also performs blind spot detection using the left and right sensors. Finally, the alarm priority is determined as non advisory, warning, or critical. Now, next is the ultrasonic module. This module interfaces with the three ultrasonic sensors. A 10 microsecond trigger pulse is generated. The echo pulse is measured using timer 2 and the obstacle distance is calculated. This process is repeated continuously for the front, left and right sensors. Now we open the UART shell.c. This file implements the UART command interface. During development, it was mainly used for testing and debugging. Using Teraterm, different commands such as changing the driving mode, injecting faults, and monitoring the vehicle status can be executed without modifying the firmware. Now, finally, we open the fault.c. This is the fault management module. This module can continuously monitors important safety conditions such as motor temperature, battery state of charge, and collision status. If any unsafe condition is detected, the system enters the fault state to ensure safe vehicle operation. Now let's build the project. This project has been compiled successfully and the binary file has been generated without any errors. Now let's move on to the live demonstration and see how the complete system works in real time. This part is no longer. So now we successfully build the project. Now we open the PICSimLab. I will just minimize it. Wait a minute. I will open the PICSimLab and this is the blue pill board which I selected. PICSimLab is a microcontroller simulation software. Instead of using physical hardware, it allows us to simulate the STM32 blue pill board along with the external peripherals. Here I already connected the three ultrasonic sensors, LEDs, potentiometers for accelerator, brake, battery state of charge and motor temperature. Now I will load the generator firmware into the STM32 simulation board. So here we see the values of speed, SOC, time to collision, blind spot detection, and front distance, left distance, right distance. So like this we load the binary file and we see the commands in virtual terminal. And next step is to create the comports. For that, I select the UART pins in PICSimLab. In this project, UART is used to transfer real-time vehicle data from the STM32 firmware to the Python dashboard. For that, I will minimize it and open the VSPE. So now I'm open the VSPE, which stands for Virtual Serial Port Emulator. Since both STM32 and the Python dashboard communicate through serial ports on the same computer, VSP creates a virtual COM port pair. One virtual COM port receives data from PICSimLab, while other sends the same data to the Python dashboard. In this way, serial communication works exactly like real embedded hardware. So now I create the COM ports and here I select the virtual pair. And next for port 1 I select the COM1 and for port 2 I select the COM4 and finish. So here are our two COM1 and COM4 are generated. So I just minimize it and again I open the PICSimLab. Here I configure the COM4. It already there, so I just save it. Now so So here we can see there is one connection. Here COM4 we already connected to the PICSimLab. So here we see the 1 by 2 means the COM4 is connected. So I just minimize it. Now I open the Teratum. Teratum is a serial terminal software mainly used for debugging UART communication. Here I will connect to the configured COM port and I will select the serial and I select the COM1 and I will go to the setup and to select the baud rate serial port and the speed must be configured as 11115200 which is the same baud rate configured in the STM32 firmware. Okay. So here we can see the output there speed, time to collision, front distance, left distance, right distance, SOC, blind spot detection, alarm, etc. As we can see, serial communication is working properly. So the system is ready to receive commands. Since Teratum occupies the serial port, I will close it now. And the same COM port will now be used by the Python dashboard. So I just now open the command prompt. From here, I will launch the Python dashboard. So here I will simply type the command. Okay, next. Okay, these are the files. So now I'm open the dashboard. So here I select the COM one, which I previously selected. So enter. So it opens the Python dashboard. So our Python dashboard is, wait. So this is our Python dashboard. So now it is continuously receiving the live vehicle data through UART from STM32 firmware. The dashboard displays all the important vehicle parameters in real time. It shows vehicle speed, battery state of charge, motor temperature, motor torque, accelerator position, brake position, estimated range, and the current ADAS warning status. As the simulation changes, these values update automatically. Now first I will increase the accelerator pedal from the PICSimLab. So for suppose accelerator pedal is 0.80 something like that. So we can see the speed is about 9 kilometer per hour. So now we increase the accelerator pedal and brake is 0, and we increase the accelerator pedal to the maximum. So we can see in the virtual terminal also. So wait, I will show you. So yeah. So like the speed is slowly starts increasing. Here it is 9 and it starts slowly increasing 10.7. So again it is 11. So it like that it increases. So here we can see initially before we saw like the speed is 9 kilometer per hour. Now the speed is slowly starts increasing, and the as we can observe here the vehicle speed increases gradually. So at the same time the motor torque increases and the battery state of charge decreases slowly. So and the estimated driving range is updated continuously. So this demonstrates the EV dynamics model implemented in the firmware. Now I will apply the brake. So we can see what happened. I think we will wait for 2 minutes. So the speed has been increased. So okay, let's apply the brake sum. Okay, no. Now we have applied the brake and let's see the what the output is. So at the same now here we can see the vehicle speed start decreasing, and same time the regenerative braking is activated and the negative motor torque is generated as we can see here. Before that we can see the motor torque is increased. Now if whenever we apply the brake, the motor torque is generated. negative motor torque is generated. So the speed starts slowly decreasing. So the simulates energy recovery during the braking. Now we can see the blind spot detection. We decrease the brake and so to see the left blind spot. So here I decrease the left sensor to see the left blind spot. So here we can see the PB9 pin means a blue indicator. Blue LED is glow. So in Python dashboard. So now here we can see the dashboard now shows an advisory warning. So this happens because the blind spot detection logic detects an obstacle near the side of the vehicle. Here we can see that. Similarly, if I move an object near the right sensor, the same advisory warning is generated. So I will increase the left sensor to see the right blind spot, and I will decrease the right sensor. Here we can see the green LED is indicated, and we can see it in the dashboard. So here we can see that the right blind spot is detected and the alarm is advisory. So in this way we can see the advisory alarm through left and right sensors. Now a forward collision warning. Now I will increase the front. Sorry. Okay. Now I will move the front obstacle closer to the vehicle. To move the front obstacle, I change the value of the front sensor. I decrease the value of the front sensor, and I will increase the right sensor. Here we can see the LED red and yellow are indicated. So we can see it in the dashboard. So the alarm shows as critical. So the obstacle approaches the vehicle. As the obstacle approaches the vehicle, the firmware continuously calculates the distance and the time to collision. When the obstacle reaches the predefined safety threshold, the alarm changes to critical. This indicates the potential forward collision. The warning is generated using the ADAS logic implemented in the firmware. In the ADAS module, the firmware continuously reads the front ultrasonic sensor. It calculates the time to collision using the obstacle distance and current vehicle speed. If the distance becomes too small or the time to collision falls below the threshold, a critical collision warning is generated. Similarly, if the left or right ultrasonic sensor detects an obstacle while the vehicle is moving, the system generates an advisory warning for the blind spot detection. If no obstacles are detected, the alarm returns to none. So, as we can see, now the alarm shows as critical and it changes the color also. You can see there. So, now, okay, here we can see the fault at 04. So, we try to change it. I will decrease the motor temperature. So we try to see what changes are there. Okay. So as we can see, every parameter displayed on the dashboard is being updated in real time. So here we can see if I apply the brake, then brake shows as 41% and the acceleration 100%. So now I will change it to the none one alarm. So for that I will increase the front sensor value. So by that we can see the alarm as none. So here we can see the alarm as none means the vehicle detects no other obstacles are nearby it. So here we can see the negative torque is generated and the fault is zero. So okay, this confirms that STM32 firmware, UART communication, PICSimLab simulation, virtual serial communication, and the Python dashboard are all working together successfully. And this is the speed history, means it shows the speed graph. So with this demonstration, we successfully verified the implementation of the EV ADAS system. The project continuously monitors important vehicle parameters, detects nearby obstacles, perform blind spot detection and forward collision warning, and displays all the information in a real-time Python dashboard. This kind of embedded architecture can be extended further for real electric vehicles by integrating actual sensors and hardware. So, thank you for watching my presentation. I hope you found it informative. Have a great day.